talking about a new function called a rational function. We've talked about several functions this year, and this is one you've probably never seen before. You don't really do this one in Algebra 1. This is your main parent function right here, and if you were to plug in some values for x and then see what y spits out, your graph would end up looking like this. And so this is the parent function that we will then be transferring around today, shifting it left and right and up and down, stretching, compressing, reflecting, and doing all those things that we've been doing for the other functions. But first, let's talk about some features of the parent function. This one is a little bit different because it has two asymptotes. We've never had asymptotes before. An asymptote is an invisible line that you can see that the graph is getting closer and closer and closer to, but never quite touching. This vertical asymptote right here is at x equals 0. We also have a horizontal asymptote on the parent function, and it is at y equals 0. So this graph will get closer and closer and closer and closer to it, but never quite reach it. How I usually describe that to students is I tell them to think about a bucket of sand. And if I said, keep taking out half, will I ever be completely out of sand? And the answer is no, because you will get down to a smaller and smaller and smaller amount. But if you're only taking half, you will never be completely out. And that's what this graph is doing. It's getting closer and closer to 0, but never quite making it. So that's how an asymptote usually functions. Now, let's talk about the domain because it's a little bit different for this kind of graph. Remember, domain asks the question, how far left and how far right does the graph go? Well, this graph keeps going left and left and left, and right and right and right, with one exception. It's skipping over 0 right here. You can see this is getting closer and closer to 0, and this is getting closer and closer to 0, but neither lines are reaching 0. So here's how we can write the domain for that. First of all, it's going to negative infinity, and it's ending in positive infinity. We established that. However, from negative infinity, it's getting very close to 0, but never quite reaching it, okay? And since it's never reaching it, we're going to use a parentheses because it's not equal to 0, it's just getting very close to 0. Then we use this U to say that there's a union, meaning there's two parts to this domain. It's going to pick back up at 0 because after it skips over 0, this piece picks up at 0, and then it's going to go on to infinity. So for this domain, you kind of have two pieces. You have from negative infinity to 0, but it doesn't include 0, and then it's going to go on to infinity. The range is going to be very similar. You can see that it's going to keep going down and it's going to keep going up. However, because of this horizontal asymptote, it is going to skip over 0 again. So we are going to have the same range. We already mentioned this before, but we have a vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0. As we do our transformations, our asymptotes are what are going to shift left and right and up and down. Let's try a couple of those. We've done transformations on several other functions. Let's review what the a, h, and k has done in our other functions. If you remember the a is usually out front, and it is the thing that stretches vertically or compresses vertically, and it can also reflect. That's what it's going to do to our rational functions. So keep in mind when a is negative, it will reflect. The h has always been the number that's going to shift the graph left and right. So this is still going to shift it left and right, but keep in mind it's going to shift it left and right, our vertical asymptote, because the vertical asymptote is going to shift left and right. For the K has always shifted things up and down, and this is going to shift our horizontal asymptote up and down. So let's see how that's going to look when we look at a problem like this. A is just 1, so we don't need to worry about any stretching, compressing, or reflecting. We have a 2. Remember, the minus is the opposite of what you think. So instead of going left 2, we know we're going to move to the right 2. So this tells me we're going to shift right to our vertical asymptote. So let's draw that in our graph. We're going to shift our vertical asymptote to the right to, right to. All right, there is our vertical asymptote. The +3 is the K, so that's going to shift our horizontal asymptote up 3. So I'm going to draw my horizontal asymptote up 3. So that's kind of my guideline for the graph. If you remember from the parent function, we had one piece, and this first point is always like in the corner here, over 1, up 1 from the asymptotes. It's going to get closer and closer to the vertical asymptote and closer to the horizontal asymptote, but just don't cross those asymptotes. We will have another point in here, and it's going to be getting closer and closer to that asymptote and closer to this asymptote. So they will always fall in these two corners unless our A is negative, then they'll fall in these two corners because we need to reflect it. So we will always keep the graphs in those two corners. So that's how you would draw the graph. Now let's talk about our domain and range for the graph. Again, it's going all the way left and all the way right. So from -infinity to +infinity. Let's pay attention to which number that the x's are not including. So notice our vertical asymptote is here at 2. So that is called a restriction on the domain because x is not included in this domain. So we're going to go from -infinity to 2. Use that union again, and then it's going to pick back up at 2 and continue on to infinity because it's really only skipping over that one number. I just want to note why there is a restriction on that 2. If you look at our equation here, if I was to plug in 2 for x here, 2 minus 2 is 0. What's 1 divided by 0? The thing is you can't ever divide by 0. That's illegal in math. And that's why it's undefined here. That's why we have a restriction on the domain. Because you can never divide by 0, we know that this number, it can be anything, but it can't be 2 because that will cause our denominator to be 0, which will cause this fraction to be undefined. All right, let's look at our range. It goes from -infinity to +infinity, and our asymptote is at 3. So that is the restriction on the range. So we're going to go from -infinity to 3, and then pick back up in 3 again, and go on to +infinity. Our two asymptotes, we have one this is at y equals 2, and this is x equals 2. Sorry, I said it the wrong way. It's cutting the x-axis. The vertical asymptote is cutting the x-axis, and this is cutting the y-axis. So we have a horizontal asymptote at y equals 3. All right, let's do one more transformation together. All right, let's look at this second example. Let's look first at our transformations that's going to take place so we can kind of visualize what the graph is going to look like. First, this 2 is in the position of the A. Remember, the A can stretch and compress. Since it's bigger than 1, we know that this is going to stretch vertically by 2. The 1, remember, it always moves the opposite direction. So the 1 is going to move the asymptote to the right 1. Left 1. I'm putting the arrow for left and I'm doing the opposite. So it's going to shift our vertical asymptote left 1. And this is going to shift our horizontal asymptote down 3. So those would be our transformations. Now let's apply it to the graph. First of all, I'm going to graph my vertical asymptote to the left 1. So I'm going to have an asymptote here. I have a horizontal asymptote that's going to be down 3. Now, the stretch is the only thing that's a little bit different here. Notice in the last example, I went over 1, up 1, and it was right in this corner. But if I'm going to stretch it vertically, then that means it's going to be shifted up a little bit. So instead of going over 1, up 1, I'm going to go over 1, up 2. It's going to stretch up a little bit. So it's still going to get closer and closer to this asymptote and closer to this asymptote eventually. I'm going to stretch it the same way this way. Instead of going over 1, down 1, I'm going to go over 1, down 2. And then have the graph get closer and closer to the asymptotes there. All right, let's talk about the domain and range. Again, we can see that the domain is going from negative infinity to positive infinity, and we're going to look for the asymptotes to see what the restrictions are on the domain. The only restriction we have on this domain is -1. We can see here an asymptote at x equals -1. So it is going to skip over -1. And again, when we look at our equation, if we plugged in -1 here, it would cause us to divide by 0. That's why we have the restriction on the domain here. Let's look at the range. The range is going from negative infinity to positive infinity again, with the exception of it skipping over -3. Let's talk a little bit about why this is causing an undefined part. So if I was going to plug in -3 for the y value, because this is talking about the range here, and if I added 3 here, so let's plug in -3. If I added 3 to both sides, I have 0 equals this fraction right here. There is no number I can plug in for x here that's going to make it spit out a 0. That is an impossible scenario. There is nothing I could multiply this by. And that is exactly why there's a restriction on the domain at -3. I can plug in any other number here for x, but I cannot plug in -3 because it's causing this to equal 0. So that is why we have those restrictions on the domain. So as you can see, the transformations are the same for rational functions. The new things that we've learned today is about asymptotes are new for us on rational functions, and paying attention to how we're shifting the asymptotes with the h and k, and the a works a lot the same. But those other things, it's similar, but it's just a little bit new of a function. And that's it for rational functions.